tuned, stay patient, and yeah, looking forward to our space today. Tuned, stay patient, and yeah, looking forward to our space today. Tuned, stay patient, and yeah, looking forward to our space today. Tuned, stay patient. Request you to share the space with anyone who might be interested in the theoretical side of science. We have string theory, very fundamental theory here, and we hope that all of you are as
You to share
interested
the space
in learning
with
about it.
anyone who might be
So,
interested. Yeah, as we
in the
wait for
theoretical side
our
of
esteemed
science
guest,
to join us,
we have string theory. Very
please do
fundamental
continue to share
theory
the
here.
space.
As we
And we
wait
hope that
for them to join
all of
us.
you are as
Request you to share
interested
the space
in learning
with
about it.
anyone who might be
So,
interested. Yeah, as we
in the
wait for
theoretical side
our
of
esteemed
science
guest,
to join us,
we have string theory. Very
please do
fundamental
continue to share
theory
the
here.
space.
As we
And we
wait
hope that
for them to join
all
us.
of you are as
Request you to share
interested
the space
in learning
with
about it.
anyone who might be
So,
interested. Yeah, as we
in the
wait for
theoretical side
our
of So I also implore the audience to write what they would like to learn about string theory from our talk today, because our guest Hassaan Saleem is definitely an expert. He's pursuing his PhD at the University of Albany, and he is definitely very well equipped to handle the theoretical side of things. But I would also like to know, where the audience's mind is at, because theoretical physics can get very abstract, and that is one of the bigger challenges of handling it. It is quite ideal as what IU speaks, right? It's very mathematically consistent, but sometimes it's about bringing the bridge between reality and abstractness, which is the challenge in theoretical physics. So, as an engineer, I have grown learning to love physics, but I would also love to, hear from our guest today. So, we would definitely be bringing him up. So, we have super conformal Hassan, or Hassaan Saleem. Welcome to our space, and we will be starting shortly. So please send out your invites, repost this space on your timeline, and send it to anyone who would be interested to join us in listening and learning about string theory. Stay tuned.
Thanks. I think we can start it now. Hello everyone.
Before we start, can I check if my mic is working? So can
Okay.
you
Yes, yeah, we can hear you.
can you listen me clearly?
Yes, it's clear.
Okay, thanks.
So I think we can start it now. Hello everyone. I am Ayush, a physics student, and it's a pleasure to welcome all of you to our ninth edition of XSpace, hosted by Team Zetagravit. Today we'll be talking with Hassaan Saleem, a Ph.D. student at SUNY Albany, New York, specializing in theoretical physics and actually theoretical high physics, with a keen focus on string theory and conformal field theory. Hassan educational path led him to the International Center for Theoretical Physics (ICTP) in Italy. It was founded by Abdul Salam, a Pakistani Nobel laureate who not only helped unify electromagnetic and weak nuclear forces but also championed scientific education in developing countries. Salam's vision for ICTP was to create a global hub, like where scientists, particularly from less developed nations, could engage in research without barriers of geographical and political boundaries. And Hassan continues this legacy of exploration and education through his YouTube channel, Phymaths, and his podcast, making complex physics accessible and engaging. Hello, Hassan. How are you?
I'm fine. How are you?
I'm good. I'm good.
Okay, so how are we going to start this? So do you want me to describe the basic concepts behind string theory, or do you have some particular questions for me?
Yeah, Hassan, we will be going through a questionnaire and you can give us, your answers, your experiences,
Mhm.
and everything. So, what the first we would like you to do is probably, give us an introduction. We have, only scratched the surface of your journey. So, I would love it if, you could share your passion and how you came about where you are. And then we can get into a bit more of the science.
Sure. Okay. So, I mean, to be honest, my journey hasn't been very long until now. I'm only a grad student right now. But if you want me to start from my undergrad, when I was in my undergrad, I knew that I wanted to do physics. And I'm sure that you can relate to this particular thing that I went through. That I have a big family, right? And all of them asked me to do engineering after my A levels, right? So I had to endure a lot of pressure to do theoretical physics instead of engineering. So that's why I knew that I wanted to do theoretical physics from the very start. And by very start I mean very start of my undergrad. And after I did my undergrad, I applied for different places. And one of the places where I applied to was ICTP. ICTP was one of the places where I could learn a lot because, before I start my PhD. So ICTP was a very good experience for me. It could have been much better, but I mean, COVID ruined a lot of things. So yeah, it was, but it was still a very good experience for me. And after ICTP, I went to, the place where I am right now, which is SUNY Albany. So I think one of the reasons why I ended up here is again COVID, because I had to give my GRE physics, and a lot of universities don't accept you if you don't have GRE physics. And I couldn't give my GRE physics because of COVID. Again, COVID ruined a lot of things. So this was one of the places where they do string theory, and they don't require GRE. So that's one of the reasons why I end up here. But I think it's a good place. I met a lot of very good people working in the field that I'm working in, and I also met a lot of I made a lot of friends here. So yeah, that's my very brief journey right now. So let's see what the future holds.
Yeah, that sounds quite fascinating. So, can you probably give us some insights into, your field in particular and the faculty at, I know COVID was a big factor, and I think a lot of us have had a lot of different things happen during COVID. But what about the faculty at, State University of New York, Albany? That still you had to do a PhD, which I think is a big task. It's a big research question that you have to take up, and theoretical physics definitely needs you to kind of have a good amount of peers that can help guide you in this journey. So how did you find it? How has your PhD journey started? And were there any other places that you considered as well? That would be a good start.
So right now at SUNY Albany, the string theory group has 2 faculty members, right? But if you include the PhD students that we have right now, then I think I would say that we have something like 8 people working on string theory or string theory related ideas, right? But if you talk about the faculty members, there are only 2 of them. One of them, primarily works on black holes and integrability, which are again big areas. The other one, who is my advisor, he works on conformal field theories, which are a very special theories in 2 dimensions and higher dimensions as well. And he also works on a topic that is booming right now in theoretical physics called the generalized symmetries. So these are the major 2 topics that he works on. So yeah, when it comes to faculty members, there are only 2 of them. But then my colleagues, which involve PhD students, they're fun to talk to. Some of them work on fields which are adjacent to my field. Uh, None of them works on exactly what I'm working on right now, but they do work on fields which are adjacent to my field. So one of my colleague works on black holes. So her work is okay. So I don't think that I can go in a lot of detail about her work, but I can just tell you very roughly what she works on. So she tries to build solutions, black hole solutions, that can be embedded into string theory, right? And the other one works on some particular theories called supergravity theories, and how to study their there is this property called integratability, which means that you can write down the solutions of a particular set of equations. So the question is that, can you always write down the solution of a particular set of equations using integrals and things like that? So this particular area is known as integrability. So she works on that. Another colleague of mine works on generalized symmetries. So that's something that my advisor works on. If you want to know more about that, I can go in a bit of detail regarding that particular thing. Another one of my colleague works on black holes again. And the last one, he works on, he does a lot of numerical work. So he works on something called conformal bootstrap, where people use numerical methods to understand these particular theories called CFDs, or conformal field theories. So yeah, these people are in my department right now, and we do have weekly sessions where one member of our string group, chooses a paper that appeared on archive, and we talk about that. So it's not like a talk; it's more like a discussion. So that gives us an opportunity to get together and talk every week. But apart from people who are in my department, I have tried to find a lot of connections with people who are not in my department via social media, and yeah, I think mainly through social media. Yes, so that has worked out for me. Not greatly, but I think I would say that it's not bad. One of the things that I got out of it was a collaboration. So right now I'm collaborating with some people who are not in my department, and that couldn't have been possible, I think, if I didn't do this outreach work that I'm doing. So yeah, that has been a small description of the journey that I'm talking about right now.
Yeah, I mean, that sounds fascinating. And, black holes are like the eternal question, right? It's a big mystery. And I think a lot of, physics and maths end up at questioning what is and how to define, black holes. So it's really fascinating to see. I'm obviously telling that, even string theory will obviously try to solve for what is a black hole. But uh, can you give us maybe some more insights into your specific thing, which you said is conformal field theory, right? So how is it? What exactly is it? Just we would probably take it light just now, and we can get into more advanced things as the questions come along. So let's get the audience caught up on the basics of string theory, conformal field theory, and why maybe you chose this specialization to, do your PhD on. That would be my next question.
So when I started my PhD, even before when I started my PhD, I I mean, even much before I started my PhD, actually, when I was doing my bachelor's at that time, from that time, I knew that I wanted to work on string compactifications. So what is string compactifications? So as you probably know, that string theory, can exist in 10 dimensions, right? And we certainly don't live in a world that has large 10 dimensions. We live in a world that has three big space dimensions and one big time dimension, right? So how to reconcile these two facts? So one of the ways in which you can do that is to make extra dimensions small. So if you have 10 dimensions, then you know um, allow four dimensions to be big, but the rest of the six dimensions have to be small, so small that our experiments cannot see them, right? So if you try to do that, it turns out that there are a plethora of ways to do that. I mean, there are many, many ways to do that, right? So if you systematically study different ways in which you can make extra dimensions small, that gives rise to this whole field, which is called string compactifications, right? So that's something that I wanted to work on, because one of the ideas that pulled me into string theory, early in my bachelor's, was the fact that you can probably calculate the fundamental constants of nature based on the geometry of the extra dimensions, right? So that's why I wanted to work on string compactifications. But the thing is that when you start your PhD, you have to understand that either you can be an independent researcher, and by that I mean that you will not get a lot of help from your advisor and people around you, or you can try to be a bit more flexible and say that, okay, so I will do my PhD on something that you are mildly interested in, and your utmost interests can be fulfilled after your PhD. So my advisor had done some work on string compactifications, but he mainly works on conformal field theories. So that's one of the major reasons why I started to work on conformal field theory, because my advisor could provide me with much better guidance if I'm working on conformal field theories. So that's why I turned to conformal field theory. But the thing is that conformal field theories are related to string theory. Actually, one of the descriptions of string theory is as a conformal field theory on a particular two-dimensional space called the world sheet. A world sheet is actually is the surface that a string sweeps when it moves through space-time, right? So for example, if you have a closed string and it moves through space-time, it will generate a cylinder-like structure, but it doesn't have to be an exact cylinder, because it can be curved and things like that. If you have an open string, then when it moves through space-time, it will generate a sheet, but it's not a cylinder anymore, right? So that's called a world sheet. And you can describe string theory as a field theory on this two-dimensional surface. And it turns out that this field theory is a conformal field theory. So conformal field theory is central to the description of string theory. So that's how I ended up working on conformal field theory. But right now I have I've gone back to string compactifications, and I'm working on two projects right now, and both of them are regarding string compactifications.
Okay, that's quite complex and hard. So let's kind of reset the room a little bit. And I want to welcome the audience again to our ninth edition of the XSpace, where we have our PhD student Hassaan Saleem, who is pursuing his PhD in conformal field theory. And our talk today is on string theory. So please do share the space, repost it, and if you have any kind of questions, please do share it in the comments. I would also implore the people on our YouTube stream to also share your questions in the comments, and we will address them at the end of the space. So stay tuned, and we will try to bring up all the speakers who have questions to ask them to the guest directly. So, yeah, let's get on with it. And I think you have been, a YouTuber as well. So, if you really had to explain this to maybe a person in fifth grade or 10th grade, a science student, right? So let's try to simplify it, because I think 10 dimensions yeah, are one too many. So we are used to maybe three, and four is like time and things like that. So there is a lot more complexity in what you just explained about conformal field theory. So let's head back to the 101, and let's see if you can help us get a better understanding of the fundamental string theory itself. and then we will try to build up to the level of understanding it where you research, because I think you have a vast knowledge base, and I think everyone is here to learn. So let's start with the 101, and then we'll have Ayush also jump in with some questions because he is the physics student here. And yeah, let's get started. So go ahead, Hassan, give us string theory 101.
So the basic idea of string theory is that previously we thought that the fundamental constituents of nature are particles. There can be different particles, but there are particles at the end of the day, right? String theory says that the fundamental constituents of nature are actually not particles, but they are extended objects like strings, right? Now there can be closed strings or open strings, but they are strings at the end of the day, right? So this is the basic idea of string theory. Now this idea may seem very innocent. I mean, of how this can change a lot of things that we know about the world. But it turns out that it's not, and it's much more difficult to work with, strings as compared to particles. So that's why a whole field, a field so dominant that it has, dominated the theoretical physics discourse in the last 50 years or so, was born out of this simple idea. Now, if you ask me the question that what was the motivation to consider such an idea, it was not, it was not to unify all the forces from the very start. Nobody said that if you want to unify all the forces, which includes gravity as well, then let's try strings. No, that didn't happen, right? So the motivation to consider this idea was that there was some data coming out of particle accelerators, right? And there was a okay, I don't want to go into technical details, but there was some intriguing feature that physicists were not able to explain using their current theories at the time. And I'm talking about the 60s, late 60s, right? So one person in Italy whose name was Gabriele Veneziano, he considered a formula that you probably know. It's called the beta function. Um, People who study physics, they know more about the beta function. I mean, I'm not talking about the beta function that appears in quantum field theory. I'm talking about the mathematical beta function. So if you take the factorial, for example, so factorial of 2 is just 2 times 1. Factorial of 3 is 3 times 2 times 1. Factorial of 4 is 4 times 3 times 2 times 1. So you know the factorial thing. But the thing is that if you want to generalize the concept of a factorial to numbers that are not necessarily integers, right? That can be done, and that is done by this function called the gamma function, right? Beta function is just a function that is made up of 3 gamma functions. It's nothing more complicated. But what happened is that Gabriele Veneziano saw that this innocent-looking function called the beta function can actually describe some of the physics that is going on, right? So he didn't come up with strings, but he came up with the use of this formula for describing that physics, right? If you want me to go into if you want me to go into a bit more detail, I can go, but I don't think that will be fruitful. Okay, so what happened later is that Leonard Susskind was a grad student. Sorry, well, not a grad student, but he had done his PhD in '65, I think. So he was a junior postdoc or junior faculty member somewhere. He came across this formula, right? And one of the things that he realized was that this formula is actually describing a string. So the physics that I'm talking about had to do with physics of the strong interactions. So strong interactions is the physics that describes the force that keeps protons and neutrons in the nucleus. So you can ask the question that if protons are positively charged, and we do know that positively charged particles repel each other, then how come protons end up in the nucleus? Why don't they just repel each other and the nucleus is destroyed? So the answer to that question is that we have another force there, which is called the strong force, which dominates this electrostatic repulsion, right? So there is this extra force that works in the nucleus, which is called the strong force. So the physics that I'm talking about that Veneziano was trying to explain had to do with strong force, right? So Susskind actually found this thing that the formula of Veneziano's formula was describing a string. And therefore, there was a time when people were trying to explain the interactions between, the particles that experience this strong force, which, includes quarks, with a string. So they were modeling quarks as if they are joined by a string. And even today, actually, there are some models where people think of quarks as being joined by a string. But later, this model went out of favor because people came up with better theories. For example, quantum chromodynamics. Now, right now, the theory that describes strong interactions is quantum chromodynamics. So therefore, the string picture of strong force went out of favor. But later, it turned out that in the 70s, people discovered this thing that string. If you take this idea of string theory, right, and explore it further, then it turns out that it always includes gravity. Gravity comes for free, and that's something that is, that is never seen before. I mean, if you study other theories, for example, or quantum chromodynamics or quantum electrodynamics or anything like that, gravity doesn't come for free, right? But in string theory, gravity was necessary. It's not something that you have to put in by hand. And when people realized that, and by people I mean not a lot of people, because not a lot of people were working on it, in the 70s. One of the major figures that was working on this idea was John Schwartz at that time. And he actually had a lot of opposition from people like Feynman, for example, because he was working in Caltech and Feynman was in Caltech as well. So when people realized that gravity comes for free in string theory, they started to think about this possibility that can we use string theory not for strong interactions but for all interactions. If we are able to somehow embed all of the interactions in string theory, then since we already have gravity here, then probably this theory can be the theory of all the interactions, including gravity. So the thing is that, okay, that seems like a possibility, but you have to show that it works, right? Otherwise, you are just speculating. So what happened is that people started to realize that there are different versions of this string theory. So for example, there is this version which is called the type 2 string theory. In this particular version, you cannot have open strings. You only have closed strings. There is this version called type 1 string theory that can have open and closed strings, right? And by the way, there is no version that has only open strings because that it can be shown that it's impossible. If you have closed strings, you have to have closed strings as well. So people had these three versions before 1984. One of them was type 1, and type 2 comes in two flavors called type 2A and type 2B. But these theories were not very well received because there were some speculations that people thought that these theories may have mathematical inconsistencies called anomalies. Now, it was easy to show that type 2A doesn't have anomalies, right? Wait, let me get this right. Yeah, type 2A doesn't have anomalies. That's true. It was shown by Witten and Alvarez Gomes. So these are two very well-known physicists, that type 2B doesn't have anomalies, right? But what about type 1? Type 1 anomalies was hard to refute. I mean, it was hard to show that type 1 doesn't have anomalies. So in 1984, two physicists, one of them was John Schwartz, and the other one was Michael Green. So Michael Green was also a Lugasian professor of maths at Cambridge University. I mean, that's actually the reason why I came to know about him in the first place, not because of string theory. So Michael Green and John Schwartz in 1994 worked this out in June of 1994, I think. And they showed that, yeah, type 1 doesn't have any anomalies as well. So it means that these problems that people had with string theory, and the problems included, the possibility of anomalies, was not something to worry about. And after their work, people refer to their time as, the first superstring revolution. So after that first superstring revolution, a lot of people started to work on string theory because they thought that, okay, it may be, a candidate for, quantum gravity at all. By quantum gravity, I mean a theory that can write down gravity in terms of quantum mechanics. But string theory is more than that. It's not just quantum gravity. It's quantum gravity plus all the other forces, right? So later in 1988, people also came up with two other string theories, which are known as heterotic string theories. So you can see that now we have 5 different string theories. So type 1, type 2A, type 2B, and there are 2 heterotic ones. I mean, I can give you their names, but I think that's not important. But the thing is that if you think that the whole, the whole universe is described by a theory, that theory should be unique, right? I mean, why would you have 5 different flavors of that particular theory? Now, before I go on, actually, there are many things that I can talk about from here, but I think one of the things that I will talk about is this. There is this problem that physicists face when they are, talking about these kind of theories. And the problem is this: if you consider any scenario where the forces are strong, then it turns out that it's very hard to solve the equations, right? If the forces are weak, which in the jargon for this scenario is weak coupling. So if you have weak coupling, which means forces are weak, then you can solve the equation. There are methods to solve the equation. But again, you cannot solve the equation exactly. You can solve the equation approximately, right? These methods are called perturbative methods, which allow you to solve the equation, when the forces are weak. So in the weak coupling scenario. But in the strong coupling scenario, where forces are strong, I mean, you cannot use those perturbative methods, which means that you just have no insight in that scenario, right? So these 5 string theories were studied in the weak coupling scenario because we could solve the equation there, and we had insight in that particular scenario. Now, in the 90s, what happened is that some physicists were trying to understand if they can find some connections between these 5 string theories, so type 1, type 2A, type 2B, and 2 heterotic ones. And it turned out that there were some connections found, but by some people. I mean, there was a lot of work that went into it in the early 90s. But one of the biggest works came out in 1995, and it was done by Edward Witten, who is a very well-known string theorist, right? So he showed, he motivated the fact that all of these string theories are actually limits of a single theory. And by limits, I mean there is a single theory, and there are at least 5 different regimes. And in each of these regimes, this single theory becomes one of these 5 string theories. So sometimes people refer to this as these 5 string theories are 5 corners of a bigger theory. I mean, they're using the word corner metaphorically, of course. There's not a literal corner. So this single theory is referred to as M theory right now. And he had to use an extra ingredient, but I don't think that I need to go in the detail of that. He used something called 11-dimensional supergravity, but that's not required. The important thing that you need to realize is that this M theory lives in 11 dimensions and not 10 dimensions. So one thing that I didn't tell you before is that string theories but most probably they live in higher dimensions. For the string theories that I'm talking about here, they live in 10 dimensions, right? So this M theory lives in 11 dimensions because it introduces an extra dimension. You can understand this extra dimension by the following insight. This extra dimension comes in the form of a circle, right? And if you look at the coordinate along this circle, you can think of that extra coordinate as the force. So if you have a strong coupling, then you are somewhere on this circle, away from the point which represents 0 force. So this extra dimension is actually nothing but the coupling or the strength of the force. So right now we have this M theory model, and we again understand this M theory in weak coupling limit, because weak coupling limit and low energy limit. Because again, if you go to higher energies, again the equations become very hard to solve, right? So in the mid 90s, when this work was discovered, or when this work was presented in the University of Southern California, I think that started this second superstring revolution. And at the very same time, there were some other realizations made. One realization was that string theory is not just a theory of strings. You need to have some extra objects in this theory, right? So one of the major works that exemplifies what I'm saying is the work of Joseph Polchinski. So Joseph Polchinski was a physicist who, in the mid 90s, showed that you need to have these extended objects called D-branes, in your theory as well. And you can think of these D-branes as the places or the planes or the membranes where the ends of open strings live, right? So if you have open strings, they have two ends. These d-branes can be thought of as boundary conditions that you put on these, ends of the open string. So, okay, that was one of the major works. But then there was another major work in the late 90s. In the late 90s, it was discovered, well, actually, there were some speculations before this work that something like this could be true. But in the late 90s, it was discovered that there is this connection, a very non-trivial connection between theories that have gravity in it and theories that have no gravity in it. Okay, so this is sometimes called the holographic duality. But one of the major things about this work was that if you understand one theory in the strong coupling limit, then you automatically understand the other theory in the weak coupling limit, and vice versa. Which means, as I told you before, that we understand the weak coupling limit very well, right? But we have problems when we go to the strong coupling limit. But this correspondence, the holographic duality, allows us to understand the strong coupling limit of some theories using weak coupling limit of some other theories. So it means that it can give us a doorway into solving the problem of understanding the strong coupling. And holographic duality has been used everywhere. I mean, not just in string theory. It has been used in condensed matter physics. It has been used in heavy ion physics. It has been used in many other. I mean, condensed matter physics itself is a very big area, and you can go into the sub areas of that particular field. So holographic duality has been one of the major breakthroughs of
Hassan,
the 90s.
I think that's quite good, and I think it's a lot to process. So let me just reset the room a little bit, and I have a little bit of a question for you here before we continue on to bringing that history of or the overview of string theory to the 2020. But welcome back to the ninth edition of the XSpace, where we, Team Zetagravit, have our guest Hassaan Saleem, a PhD student at the University of Albany, New York, is working on string theory and conformal field theory. So, if you are interested in learning, please do tag along with us and share your questions if you have any in the comments. Even this is a request to all the YouTube streamers who are listening in. Please do share your questions. And ultimately, I think we want to continue this conversation, Hassan. But the question is, how has, I think we have spoken a lot about the theoretical physics being the framework, right? But you kept using this word discover. So, were there any experimental physics revelations that kept fine tuning the theoretical physics frameworks and vice versa, right? How has the dance between the experimental side and theoretical side kind of guided this development of what you call, string revolutions and things like that? So, if you could give us some more insight into that, if you have anything for us, that would also be helpful in us understanding, a lot of this abstract theory physics.
Sure. Okay. So the thing is that even before you came up with the idea for string theory, so the problem of quantum gravity is very old. I mean, some people knew about this problem in the 30s, 30s or 40s. Even before you come up with the idea of string theory, you could ask the question that if you have any theory of quantum gravity, how hard would it be to test it, right? And the answer to that question is not unique to string theory. It's unique to any theory of quantum gravity. You mean any theory that we know or any theory that we don't know, right? Because gravity is much weaker than the other forces, right? We do know that if you want to directly test quantum gravity, you need an accelerator that can give you the energies called the Planck energy. And Planck energy is something like, if you are familiar with these units, the Planck energy is almost 10 to the power 19 GeVs, right? GeVs means giga electron volts. Giga means 10 to the power 9. An electron volt is the kinetic energy that a single electron gets when accelerated in a voltage of 1 volt, right? So that's, a unit of energy that physicists use, right? So that's a very big energy, actually. Right now, our biggest collider, which is Large Hadron Collider in Geneva, It can go up to 13 TeVs, which is 13,000 GeVs, which is almost 1.3 times 10 to the power 4. I mean, 1.3 is not that important. 10 to the power 4 GeVs. We want to go to 10 to the power 19 GeVs, which is 15 orders of magnitude high, right? Okay, so if you want to pick a collider which can give you the energies of 10 to the power 19 GeVs, how big does it have to be? So Large Hadron Collider is almost 10 to the power, sorry, it's almost 27 kilometers in circumference, right? It turns out that if you want a collider that can take you to 10 to the power 19 GeVs, right, it has to be as big as the Milky Way galaxy, right? So here's the answer, but this answer is not unique to string theory. This is a problem with quantum gravity. And this number is so big, this collider is so big because gravity is much weaker than the other forces. So if you want to have energies that can go probe gravitational interaction, to the extent that we want, you need an accelerator that is as big as the Milky Way. Okay. So this problem is a problem that all theories of quantum gravity will suffer from, right? Okay. I'm addressing this point because whenever string theorists talk about this particular problem, people say that, okay, then your theory is not testable. First of all, that's not true. And secondly, this is a problem not just of string theory. I mean, even loop quantum gravity or any other theory of quantum gravity will suffer with this problem. It's not a problem of string theory. It's only a problem because Planck mass, or okay, let's not talk about Planck mass. It's only a problem because gravity is much weaker, right? Okay. Now, are there some other experimental observations that we can do? So yeah, there are some observations that we can hope to do. One of the observations is the observation of something called a cosmic string. So a cosmic string is a string-like structure in the universe that we can probe using different methods. So I'm not an experimental physicist, so I cannot give you the details of that. But the basic idea behind a cosmic string is that if there was there were some strings in the early universe, when the universe expanded, it can happen that there were some defect-like structures or some strings that got expanded with the universe, and right now they are out there somewhere. We don't know where they are, but they can be somewhere in the universe. So if we can somehow detect those strings, it can give us some credence, or it can give us some hope that string theory is right. I'm saying this because detecting a cosmic string doesn't necessarily tell you that string theory is right, because you can have cosmic strings even in quantum field theories. So for example, if somebody is interested, I would invite you to look into something called a Nielsen-Olsen string. So a Nielsen-Olsen string is a structure that exists in some quantum field theories that has nothing to do with string theory. But it can, it can be a string theory string, right? So we will have to, we will have to determine if the string that we are seeing is a quantum field theory string or a string theory string, right? So that's another thing that some people hope to achieve, but I don't know if what is the state of the art on that, because I'm not an experimental physicist. One area where it has given us some results is the following. So as I was talking about the holographic duality, one of the ways in which you can realize the holographic duality, let me recall what it was. So holographic duality gave you the correspondence between a gravitational theory and a non-gravitational theory, right? So one of the ways in which you can achieve this is something called ADS-CFT. And right now my video is not on, my shirt says ADS-CFT right now. So ADS-CFT means that you have a particular space-time on one side, which is called the ADS space-time. Now ADS means anti-de Sitter. It just means that the cosmological constant is the inbuilt energy of space, right? That the cosmological constant is negative. It just means that, right? So that's ADS space-time on one side. CFT means that you have conformal field theory. I think this is something that we talked about in the start. So conformal field theory is a particular kind of quantum field theory. It has nothing to do with gravity, right? It's a non-gravitational theory. But ADS space-time is a gravitational theory. I mean, if you want to have some theory on ADS space-time, you will have to talk about gravity. Okay, so ADS-CFT is one of the ways in which you can achieve holographic duality. Okay, now why am I talking about this? I'm talking about this because there was this problem, and the problem is this. I'm pretty sure you know about. Okay, let me explain what it is. So there is something called quark-gluon plasma. Quark-gluon plasma appears when, in some sense, you literally melt the protons and neutrons. So it is sometimes said that quark-gluon plasma is the hottest possible thing in the universe because as things become hot, things start to melt, right? And what is the ultimate thing that you can melt? Well, the ultimate thing that you can melt is our protons and neutrons themselves, right? So when you, in some sense, melt protons and neutrons, then at the end of the day, you get something called free quarks. No, not free quarks. I should not say free quarks, but quarks and gluons. So gluons are the particles that carry the strong force, and they are in a plasma-like structure. So this is something called the quark-gluon plasma. But the thing is that quark-gluon plasma can act as a fluid. So you can ask questions about quark-gluon plasma and the same questions that you can ask about a fluid, right? Okay, so one of the things that we ask, that we can calculate for fluids is viscosity, right? I'm sure that any person who has studied high school physics knows what viscosity is. Viscosity is a measure of how thick a fluid is, right? So you can, try to calculate the viscosity of a quark-gluon plasma. Now, some
I think there is some problem in connection of Hassan. I think there is some network problem connection here. Wait some moment. Guys, don't worry, we will be starting in few minutes. Just there is some technical issue going on. Yeah, can you hear me?
Yes, I can.
Okay, okay, great.
Oh, did I drop?
Yeah, there was some problem, I guess. So we
Okay,
can start
so
again.
sure, but where was I when I dropped? Okay, so from where should I start? Where was I when I dropped?
Okay, so we can start with some other question, I guess. There is a question from audience coming.
Okay.
So he's asking, after learning relativity and QFT at master's level, can we start looking into concepts of string theory? What are the first few things taught at the beginning of a general string theory course? So this question is from YouTube, theoretical
Okay.
detective arcade. Yeah.
Okay. So you said that after learning relativistic quantum mechanics or something, or after learning
Yeah,
what?
he asks that after learning relativity and quantum field theory at master's level.
Oh, okay. I see. So you have learned quantum field theory. So I think now you can learn string theory because I always, recommend this to people that don't start learning string theory without learning quantum field theory. So if you have learned quantum field theory, then I think, yeah, you can start to read Polchinski, for example.
Oh, interesting, interesting. So you were talking about extra dimensions, right?
Mhm.
So why we need extra dimension in string theory, and can we see them? Like I can only imagine three dimension like x, y, and z, and time sometimes, yes, time. So why we need extra dimension in string theory? Will you explain it?
Well, sure. It turns out, okay, first of all, I think I too can imagine only three dimensions, right? Not more than that. The thing is that in order to make the maths of string theory work, you need extra dimensions. Now, I can go into some detail if you want, but um, that will require some background. But the thing is that if you don't have extra dimensions, well, okay, let me make this point clear. Having extra dimensions is one of the ways in order to make the maths of string theory consistent. There are other ways, but those ways are not very popular in the string community. The most popular way is to have extra dimensions. If you don't have extra dimensions, then there are some mathematical inconsistencies which are called anomalies. I think I was talking about anomalies before. So there are some anomalies that come into play. So for example, there is this thing called while anomaly. While anomaly comes into play if strings are moving on space-time that is not flat. If space-time is curved, then while anomaly will come into play. The the way to cancel this while anomaly or to make this anomaly vanish is to have extra dimensions, right? And if the person who asked the question wants me to go into a bit of detail, I can go. Let me know. Can you hear me?
Okay, so there is another question coming from our Parth Pandya, a co-founder of Zetagravit. So he's asking what kind of activities or projects one should plan if they want to pursue theoretical physics in higher studies.
Yeah. So were you able to listen to my answer, or should I do it again?
Oh, okay, can you do it again? I guess.
Sure. Okay, sure. So what I was saying is that if you don't have extra dimensions, then there are some anomalies that come into play. One of the anomalies that comes into play is something called while anomaly. So while anomaly comes into play when strings move on space-times that are curved, which are not flat, right? So if strings move on curved space-times, there is this anomaly called while anomaly that comes into play. And the way to have this anomaly go away is to have extra dimensions. Uh, Now, the person who asked this question, if that person wants me to go into a bit of detail, I can go. Let me know that how does extra dimension cancel this while anomaly. But yeah, while anomaly is cancelled by extra dimensions. That's why we have it. Otherwise, we will have mathematical inconsistencies.
Interesting, interesting. So I guess there is some debate going on Twitter from figures like Sabine whether high energy theoretical physics, especially in areas like string theory, is moving in a productive direction or it's lost in mathematical beauty. So what's your take on this debate?
Well, it's not a debate. I mean, Sabine is just a very bad faith critic. She's not even a critic. She does it for
So,
money. I mean, the thing
do
is
you
that,
think? Okay,
mhm.
continue,
Well,
continue.
here's the thing. So there are some criticisms on string theory which are fine, right? For example, criticisms for people like Carlo Rovelli. I mean, I respect them. Criticisms for people, some criticisms from people like Roger Penrose. I respect them. Um, and most of the criticisms that these people do are okay. String theorists know about those criticisms themselves, right? Most of the string theorists will agree with you. But if you start to say these kind of things, that string theorists are they don't want to make progress, they are just doing it to show that they are making progress so that they can have grant money coming in. This is something that Sabine says. This is something that Kurt J. Munger says, for example. I just don't like it at all, because and the thing is that I have a podcast episode coming with Zohar Kumar Korsky, who is a physicist at Stony Brook University, and we do talk about this particular point in detail. So these kind of criticisms are they're just not criticisms. They're just um, we should not engage with them, right?
Yeah, yeah. So I guess thank you everyone for joining us. And before moving into next question, thank you, Hassan.
Sure.
So there is another question coming from our audience. Do you think string theory will have a successor in the future?
It can have. I mean, the thing about theoretical physics research is that it's very hard to predict what will happen in the future. So string theory can be a jumping board for another theory to start in the future. That can happen. So I don't know. I mean, let's see.
Yeah, that can happen. Yes, that can happen. So there is another theory which is loop quantum theory, loop quantum gravity. So what is the difference between string theory and loop quantum gravity?
Sure. So loop quantum gravity. The biggest difference I would say is in their aim. So loop quantum gravity is what it says. It's a theory of quantum gravity, right? As I told you before, that string theory quantizes gravity. So quantizing gravity is a problem, right? And quantizing gravity with every other force in the same theory as well is another thing, right? So loop quantum gravity is a theory of quantum gravity. It quantizes gravity. That's it. It doesn't have every other force in it, right? But that's fine. That's not a problem, at least. So loop quantum gravity is a theory. I think this is something that if I take a teenager and I ask them that what is your idea of quantized gravity, I think the idea of loop quantum gravity may be the first thing that comes to your mind. Even a teenager will guess it. I'm not demeaning loop quantum gravity by saying that. I'm saying that it is the most obvious idea. It's the most natural idea to quantize gravity. And the idea is that space-time itself is not continuous. It's discrete. It's made up of discrete points. It's made up of discrete. I don't know how to use the word sections, right? Something like that. So it's made up of networks. For example, spin networks is the thing that they use in loop quantum gravity, right? So it's a theory of quantum gravity, but it doesn't have every other force in it. Now, what's the problem? Well, the problem is that they take Einstein-Hilbert action. Einstein-Hilbert action is the defining thing for general relativity, which is our theory of gravity, right? They take Einstein-Hilbert action and then assume that this will continue to be the case. This will continue to be the theory, even for very small distances. And I think there is no reason to believe that. So that's one of the major things, the major, mistakes that they do at the very start. I mean, it's not something that they do, at some technical point. It's the starting point. The Einstein equation for gravity, but it does predict corrections, which we do expect, to appear due to quantum mechanical effects. So string theory does not, assume that you have only Einstein-Hilbert action or the Einstein equations. It includes corrections as well, which is something that you will expect to have due to quantum mechanical corrections. So that's one of the problems with quantum gravity. There are some other things. For And that particular result has a contradiction between string theory and loop quantum gravity. So it means that if one of these theories is right, then only one of them can be right. Both of them can't be right. And by the way, if somebody wants to have a look into the result that I'm talking about, there is this paper by Ashok Sen, actually, because this contradiction was actually discovered by Ashok Sen in his paper in 2012, if I'm not wrong. So if you want, I can give you the link to that paper. But yeah, there is a contradiction between string theory and quantum gravity. Simple contradiction.
Yeah, interesting. So there is one question coming from my friend Rohit. So he is asking. Okay, wait a minute. So he's asking, can you please tell again the prerequisites in mathematics to study string theory? Do math needed for general theory of relativity is sufficient?
Okay, so that math will be essential because you need general relativity to study string theory. I would say that, so I see a lot of people are intimidated by the maths used in string theory, and that is one of the things that refrains them from studying string theory. I would say that don't be intimidated by the maths, right? Because in order to understand the basics of string theory, you don't need to be a mathematical gymnast. You don't need some esoteric maths to understand the basics of string theory. If you can understand quantum field theory, if you can understand general relativity, I think you're good to go. There are some mathematical results that you will need, but I think you don't need to understand them as a separate thing. If you start to read, for example, Polchinski, right? They will tell you. So Polchinski will tell you the required mathematical results, and there are not a lot of mathematical results that you need. Every good string theory textbook will tell you the mathematical results, in that book, in that very book. You don't need to start learning maths just for starting to learn string theory, right? So don't get intimidated by the maths. There are some areas where you will need more esoteric maths. For example, if you study this theory called F theory, which is again inspired by string theory, there you will need some results from a particular area of maths called algebraic geometry. But that's not the basics of string theory. You can learn the basics of string theory without learning a lot of maths, right? You will need to do a lot of calculations, but you can do those calculations. They are not those calculations are not coming from some esoteric maths, right? So I would say that don't worry a lot about the required maths to learn string theory. If you can understand quantum field theory, and if you can understand general relativity, I think that's enough.
Okay, nice. Do you think it's possible to approach in the field without it, without mathematics?
Not without mathematics, but not without. I'm saying that you can approach it without additional maths. So if you understand the maths of general relativity, which is tensor analysis, right? And if you understand the maths of quantum field theory, which involves tensor analysis, but some partial differential equations as well. But I think sometimes even that is not needed. So yeah, I think you don't need additional maths. That's what I'm saying. You need maths, but not additional maths.
Yeah.
Okay, here's the thing. So the only mathematical result that you will need to understand is given in, that result is given in string theory textbooks. That result is about something called the Euler characteristic, which is a topological quantity. Now, don't be intimidated by that, because there is only one result that you need to know. And the result is that what is the Euler characteristic for a surface that has G handles? For example, if you think of a donut, right? Donut can be thought of as a sphere with a handle, right? Because you can deform it, make a donut, right? So you have one handle. The Euler characteristic for this will be 0. For a sphere, there is no handle. So the Euler characteristic for this will be 2. And the formula is that Euler characteristic is 2 times 1 minus g. That's it. I think that's one of the non-trivial maths results that you will need. You don't need any other esoteric maths for understanding the basics of string theory.
Yeah, interesting. So before moving, I would like to thank everyone for keep with us. So you were talking about CFT. Okay. So how does CFT differ from QFT, like quantum field theory?
So CFT is a quantum field theory, but it's a special quantum field, right?
Okay.
It's a special quantum field theory because the thing is that if you have taken a quantum field theory course, right, the basic symmetries of space-time that people assume before studying quantum field theory include translation symmetry. So it means that if you have a translation in the time direction or any of the space dimensions, right, the theory should not be different. It's a symmetry, the translation symmetry. And you also have rotational symmetry, right? You have rotation symmetry, and you have something called the boost symmetry. Now, these symmetries make up the group called the Poincare group. So it's sometimes referred to as the Poincare symmetry, which includes translations, rotations, and boosts. Now, CFTs include all of this, right? They include Poincare group, but they have some extra symmetries. So one of the symmetries is the scale symmetry. Now, scaling symmetry is not there in Poincare symmetry. Scaling symmetry means that if you scale the whole universe with a factor of 2, for example, or shrink the universe down with a factor of 2, for example, your theory should be the same, right? I mean, the laws of physics should be the same, under this symmetry. So conformal symmetry has Poincare symmetry and more, right? So the thing is that you can think of conformal symmetry as ordinary relativistic quantum field theory plus some extra assumptions, and those extra assumptions make things simpler, actually, right? So this is what I would say, that conformal field theory is a QFT with some extra assumptions.
Oh, nice. So, someone asking, how are Calabi-Yau manifolds studied? Do we need computers to study them, or just we can do it with paper or pen?
Sure. Okay. Well, so first of all, if someone doesn't know what Calabi-Yau manifolds are,
yeah, we would like to know about that.
Sure. So I think some time ago I was talking about the thing that I work on, which is string compactifications, right? So I told you that if you have a 10-dimensional space-time, we do understand that we live in a 4-dimensional space-time. We can see 4 dimensions, right? Which is 3 space dimensions and 1 time dimension. So what to make of the extra 6 dimensions? And I told you that there are multiple ways to make these extra 6 dimensions small. Right? We have to make these extra 6 dimensions small somehow, but there are multiple ways to do it. Now, if you want to get a realistic theory out of string theory, then it turns out that you have to make this extra 6 dimensions small to make a particular space called Calabi-Yau space or Calabi-Yau manifold, right? So you can think of Calabi-Yau manifolds as the space made out of these extra 6 dimensions, right? Now, how do you study them? Well, so it turns out that it depends on what you want to study about Calabi-Yau manifolds. So if you want to study their topological properties, for example, you can do that with paper and pen. But if you want to classify them, there are some computer programs that people use in order to classify them. If you want to study strings on Calabi-Yau using numerical methods, so which means that you don't actually solve the equation, you just solve the equation numerically, which is not exact, but it gives you some insight. And then again, you would need computers. So it depends on what you want to study. If you want to study, for example, if you want to compactify, your string theory on a Calabi-Yau manifold, which means that make extra 6 dimensions, small, so that they make a Calabi-Yau manifold. Most of the calculations were done by hand. I mean, these calculations were done in the 80s. I mean, sometimes 90s or in early 2000s. They were done by paper and pen mostly. I mean, at that time, Mathematica didn't exist, so of course people didn't use it. So yeah, but right now people are using some computer programs to classify Calabi-Yau manifolds based on their properties, and those properties are called Hodge numbers. Yeah, so for those classification problems, you need good computers.
Yeah, before moving into next question, I would like to thank everyone. Please comment your question and do share this space with your friends. Okay, so the one question is coming from Parth Pandya. So he's asking what kind of activities or projects one should plan if they want to pursue theoretical physics in higher studies.
I'm sorry, I didn't understand the question. So the question is that what kind of projects should you plan?
Yeah, should we plan if someone want to pursue high theoretical physics in higher studies?
I would say that that's a very personal thing. I mean, I don't think that there is a universal answer to this question. If you want to well, I mean, it depends on what you want to work on. So for example, if you want to work on strict compactifications, for example, the thing that I'm working on, I would say that you familiarize yourself with some of the methods that people use there. If you want to work on generalized symmetries, I would say that, I mean, there are many, reviews of generalized symmetries. I mean, I have a whole Twitter thread for reviews of generalized symmetries. You can start reading one of those reviews. I would say that one thing that I see a lot of young scientists, one of the mistakes that I see a lot of young scientists make is that they put too much emphasis on papers. You don't need to write papers to get a PhD position. I mean, if you have a strong background knowledge, that will go a much, longer way than having a paper, right? So you don't need to think about projects. You just need to think about building your background knowledge, because that will allow you to do much better research in the future. So that's one of the things that I can say. I think this is a universal answer, but I think other than that, what kind of projects? I think there is not a universal answer there.
Yeah. It's a personal thing. Yeah. So I am also into astronomy. So I have a question. So I have a question. Can it be provides into early universe? Like, can it connect with dark matter or dark energy? Could it answer any open question in cosmology or particle physics? Like,
Okay, so yeah, certainly. So if you are interested in studying dark energy and dark matter from the standpoint of string theory, there is this idea that some people are working on. So we don't know if this idea is correct, but I think a lot of people work on this idea. And this idea comes from one of the leaders in string theory right now, which is Kumrun Wafa. This idea is called the dark dimension idea. So this idea was born out of some insights regarding string theory and how theories of quantum gravity work. Right? So this dark dimension idea gives arguments for the possibility that dark matter and dark energy may have a connection, and they both come out of this one single extra dimension, which is called the dark dimension, right? So if this idea is true, we don't know if it is true or not, right? Then it can be a big thing. Because the thing is that the particular insight that I'm talking about is that if you have extra particles that come into play, there is some scale of energy or some energy scale that should go really, really small. And if you think about dark matter, it can happen that they are made of extra particles that we don't know yet, right? And if you think of dark energy, that's if you try to model dark energy as a cosmological constant, then it's nothing but a very small energy scale. So in this sense, they may be connected. If you want to know more about it, you can either read a review on dark dimension by Wafa and his collaborators, or I would advise that you can you see Wafa's podcast with Sean Carroll. I think there's a very good description of this idea of dark dimension, right? If you talk about early universe, well, there are a lot of people who work on early universe using string theory. That is something that I know some things about, but I'm not an expert there. So I can tell you that there are some insights that people work on. For example, people work on some inflationary models that can explain the very early moments in the universe. But I would not pretend to know these things very well because I don't.
yeah, that's really interesting. Can you suggest some books, yeah, which for undergraduate students who want to study it, and like any research paper or something?
So for what?
No, if they want to study string theory.
Okay, so if you want to study string theory, I think you can either start with David Tong's notes. So David Tong has these notes that he used to teach in part 3 of mathematical tripos at Cambridge University. Those notes are about 215 pages long, if I'm not wrong. But the thing is that those notes will not teach you about. But the thing is that that's fine, because there is this other string theory that I didn't talk about, which you have a lot of time. But I think going to that journey is worth it because Zoibek is a very good teacher when it comes to writing as well.
Yeah, I guess before moving to, so we can have a fun and wrap up questions.
Sure.
So, what's your favorite equation in physics?
What's my favorite word?
What's your favorite equation in physics or mathematics?
Oh, that's a hard question to answer, actually. I would say that, yeah, I think I would go with, well, okay, so the cliche answer to this question when it comes to physics is either Einstein's equation or Schrodinger's equation. Yeah, but there are some answers that I want to give, but I think they will not, paint a very good picture. Some people tend to give the answer. Okay, some people choose the equation that they use on a daily basis. So, for example, in my daily routine, I use a lot of equations from string theory, but I don't want to quote them as my favorite equations because, again, string theory is not tested until now. So, yeah, I would resort to the default answer, which is either Einstein equation or Schrodinger equation. I would say probably Schrodinger equation. Well, wait. Yeah, Schrodinger equation. If you want me to resort to a bit more complicated physics, then I would say probably standard model Lagrangian. That's a very, very good equation. Yeah.
Yeah, like the Euler equation is one of my favorite ones.
Sure. Yeah. In maths,
So,
Euler equation is very good. Yeah.
yeah. So, if you could meet any physicist from history, who would be and why?
Well, okay. So there is one physicist that I would want to meet. I mean, there are multiple, but if you have asked me for one. So yeah, it's a very hard question to answer again because there are multiple people that I would want to meet. But okay, so if there is one person that I would want to meet, I need to make sure that I will be able to communicate with him because that person came from a very different time. Although he speaks English, so that's fine. But I think the English of that time was very different. So I would really want to meet Isaac Newton because I think he's one of the smartest people that walked on this planet. One of the smartest people. If you gave me three options, that I would say Isaac Newton, Leonhard Euler. If you have asked me for a mathematician, I would have picked Leonhard Euler, but Leonhard Euler also did a lot of physics work. And the third one is actually a physicist who died 3 years ago, but I couldn't meet him, so it's Stephen Weinberg.
Yeah. Who will not want to meet Isaac Newton?
Sure,
Yeah.
of course, yeah.
So, what's one book or paper that has deeply influenced your thinking?
Well, I don't think that, okay, so some papers are very interesting to read, but I don't think a paper influenced a lot on my thinking. Again, that's a hard question to answer. So the thing is that if you ask me that how did I come to physics, I mean, I didn't want to come to physics from when I was a child. I actually wanted to go to maths, right? So one book that pulled me into physics was A Brief History of Time by Hawking. So I think I would say that Brief History of Time by Hawking was one of the paradigm shifting books for me. But if you ask me about technical academic books, then I would say that probably Pascal and Schroeder. I think that's a very paradigm changing book for me. Pascal and Schroeder quantum field theory. I think I have read that book multiple times. There are some parts of that book that I still have to read, but I think the parts that I have read, those parts six to seven times. So I've been reading that book since 2016. So it's almost 8 years now.
Yeah, Brief History of Time is also one of my favorite book. Also, my
sure.
So earlier joking, Mr. Feynman is also a good one, I guess.
It's good, yeah. I mean, I read that book in 2015, I think. But yeah, I mean, at that time, I was already into physics, so it was not as influential for me as A Brief History of Time. I mean, Brief History of Time was such an influential book for me that before reading that book, I didn't even know that we can ask certain questions. And Brief History of Time actually opened my mind to make me realize that there are these questions that I think are impossible, or not impossible, but they are not useful to ask, can be asked, and they can even be answered using physics. So yeah, I mean, the thing is that I read Brief History of Time at a younger age as compared to when I read Surely You're Joking. So yeah, Brief History of Time was, I think, one of the most influential books in my life.
Yeah, because now, Surely You're Joking, Mr. Feynman is a kind of biographical book, not a science book.
Yes, it is. Yeah.
So I think it's time to end the space. Thank you, Hassan, for taking us on this journey through the cosmos.
No problem.
Again, thanks to everyone for joining us today. That brings us to the end of this edition of XSpace. On the behalf of Team Zetagravit and all our listeners, I want to thank Hassan for sharing his insight and experience with us. And you guys should subscribe his channel, Phymaths Podcast, on YouTube. That is one of my favorite channel on YouTube. And
thanks.
And if you enjoyed today's discussion, stay connected with us for next XSpace. Thank you, everyone, and see you next time.
Yeah, and
thank you.
I would definitely ask you all to share this on your feed for anyone to listen in about string theory. I think there are some things that people wanted to re-listen to. So I would ask them to check out the space again and listen to the parts that they found the most interesting. And our next edition will be the 10th space, which will be probably a mega space. So stay tuned. It is our first space in 2025. So yeah, follow Zetagravit for more. And thank you everyone for coming to the space.
Okay, thank you.
Thank you, Hassan.
Yep, thank you, sir.
My pleasure. Okay, goodbye.